Hello, my name is Faison Chell. I am currently a third-year student at Bolton University studying game programming, and in this video I'll be going over my major project, which was based on computer graphics. The aim for this project was to create a scene using a custom renderer using OpenGL with models that were created in 3D modeling software such as Blender. My project was created in the span of 2 months with no prior knowledge in graphics programming. I chose to do this project because I have an interest in low-level programming, and engine development has always fascinated me. But this is the first time I have taken the time to research and create a project, as I wanted to challenge myself and push the boundaries of what I could achieve in such a small amount of time. Within this scene, there are currently 12 models loaded. The floor and walls are created from basic cubes that have been assigned custom textures, and there are 4-point lights that are scattered in each corner of the room. As I wanted to make my scene interactive, I created a user interface that allows a user to interact and change values of these lights, including the color and position. Along with these 4-point lights, there are also 2 other light types that are present, and these are directional light, which acts as a sun, and a spotlight that acts like a flashlight. Another thing to note, I've also included the functionality for one of the models. The user can move, rotate, and scale the object. This decision was made so the user has a general idea of how the scene was put together and how the properties of lighting can affect a model. Here is a simple visual diagram of how my renderer is structured. The main engine class does all the heavy lifting and is where the rendering loop and processing is done. Each scene object is assigned a lighting shader within its own class. Once the object has been created within engine, it is assigned values that allows it to have different visual properties, as well as assigning the position and rotation of the object. When creating my objects, before I could load any models, I needed to understand the basics of graphics programming. To do this, I learned the crucial steps to rendering an image on screen through the use of vertex arrays, vertex buffers, and element buffers. Here is a diagram on the stages and how the arrays and buffers interact with each other. Vertex array objects hold the coordinates and attributes of each vertices and is used to create shapes. Some of these attributes include color, texture coordinates, and normal coordinates. Vertex buffer objects are memory reserved on a graphics card. It takes as much data as it can hold from the vertex arrays and outputs the data along with its attributes. Without an element buffer object, the vertex buffer will output all the data as a list, and as a result of this, it can only create primitive shapes. However, an element buffer is used to specify the order of vertices. This prevents duplicating vertices and allows more complex shapes to be created. The image on the left is an example of how I set up my cube vertex array. It contains 3 properties: positions, texture coordinates, and normal vectors. The positions of each vertex is essential as it tells the graphics card where each vertex should start. The texture coordinates, also known as UVs, determine what direction the texture should be facing. If these are incorrectly mapped, the textures and the shape will appear jumbled and inconsistent. The third and final property is the normal coordinates. These coordinates are for how light interacts with the object and represent the direction the object is facing. The image on the right are the cube indices used for the element buffer object. Each number corresponds to its respective vertex within the list. These indices allow me to create and construct complex shapes without the need to alter texture coordinates and normals. However, in this example, the indices are used for creating a textured cube that reacts to lighting. Lighting in computer graphics consists of three main components. These are ambience, diffusion, and specular. We can see in this image how each component affects the object. Ambience is the indirect lighting of a light source. The best way to visualize this is imagining you're in a dark room. The room is dimly lit, but it's not lit enough to see the details. But you can still make out the silhouette of the object along with the color it should be. The diffuse component applies direct lighting to the object. It's its brightest where the light hits, and it slowly dims as it gets further away from the light. And finally, the specular component. This component highlights the brightest parts of an object, and it's used to apply shininess to a surface of an object. This snippet of code is how I implemented the directional light, which is one of the three light types that exist in my project. Lighting was one of the biggest tasks, and it took me the longest to implement, as I struggled to grasp the idea of how it worked. However, after watching multiple videos and researching the topic, I understood it well enough to fix the issues I had encountered. From this code snippet, you can see the diffuse, ambience, and specular components are all calculated separately, and at the end, they are all added up to give the final result. With the addition of my UI, the user can experiment with the directional lighting, changing the angle in which the light hits, the color of the light at each component. Once the lighting shaders were done, I needed to assign values to them so they can manipulate the properties of the lighting. Shader code in general is quite unique, as it uses different programming language than C++, although it is very similar. It uses a language known as OpenGL Shading Language, or GLSL. Because of this, I couldn't just assign the values directly, and instead, I needed to point to the location of where memory should be stored, so it could be used by the shading language. This code snippet shows how I managed to do this. First, the location address is stored within an unsigned integer variable, and using the ID of the shader I'm using. Once this is done, I specify the type of variable it is, in this case, a full float vector matrix, and it assigns a variable I want to assign to the shader, which is the projection, view, and model matrices. These are used within the shader for the coordinate spaces, and without them, they may fail to render at all. At this point in the project, I understood the basics of how shapes are created, and I had lighting implemented to make my scene look more interesting. However, it still looked rather empty. So, to fix this, I learned how to load models in my project with the help of the assimp library. Before I could implement this, however, I needed to learn the quirks of each file format. This diagram shows the structure of how assimp passes through the model formats, such as FBX and OBJ. At first, this looked rather intimidating. However, upon a closer look, they are already things that I've learned and implemented in the past. The meshes have vertices, normals, indices, and texture coordinates, and each one was split into a child node, so it wasn't one big vertex array, but rather a group of small ones linked together to a root component. The easiest way I learned to implement this was to create two separate classes. A model class that had the specific function of passing through file formats and assigning its textures. And the second class is the mesh class that would process the parsed vertex and indices data and render the shape onto the screen. This code snippet shows how I implemented compatibility for glTF, FBX, and OBJ file formats. After hours of trial and error, I learned that each format has specific flags it should be assigned, and without them, the models don't look quite right. An example of this is this bag model. The reason why the textures were jumbled on the left was because the code was incorrectly reading and assigning the texture coordinates, and once I realized this, the fix was rather simple. It was assigning the texture coordinates as normals and normal coordinates as texture coordinates. This was because of a small mistake within my code when assigning it to my vertex shader. Within the code snippet on the left, you can see that each attribute is assigned a numbered location. 0 corresponds for the vertex position, 1 for the texture coordinates, and 2 for normal coordinates. And in the code snippet on the right, you can see how the OpenGL function points to one of those numbered locations. The problem arose when I accidentally assigned texture coordinates to location 2 instead of 1. Once this was fixed, it did not take me long to realize textures would continue to be an issue, and this is because of the way that models were exported. All the models that are in my project were found online, and for file formats such as FBX, the texture file paths are embedded within the model files, or the binary files for glTF file format. Of course, I could have used a 3D modeling software such as Blender or 3ds Max to manually reassign the texture paths. However, I found this to be rather inefficient and time-consuming, as I would have to do this for every model within my project. So instead, I made my own system. This snippet of code takes an old directory for the texture and passes through it until it can find the texture file name along with the type of file it is, such as the JPEG or PNG file formats. Once it has this file, the user can then set a custom directory to wherever the texture assets are located on the computer. And after rigorous testing, I've learned that not only did it make it more time efficient, but also managed to fix the models that would not load prior, due to small subtleties such as using backslash instead of / after exporting. As previously stated, I wanted the users to be able to interact with the lighting in my project to gain an understanding on how light can affect how an object looks. But to do this, I needed a way for users to be able to easily change values within a project. Sure, I could have had users manually hardcode the values and reset the application each time for changes to take effect. This would have worked, but it's not exactly user-friendly, so I decided to create a user interface through the use of a library known as Dia imGUI. When implementing the UI, I initially had a lot of difficulty with setting it up. When a new library is integrated into a project, it usually requires the code to initialize the API before it can be used. Here are a few examples of some of the initialization code within my project. If an API was to be used before initialization took place, it would fail to compile. So after I integrated imGUI into my project and did the initialization, I continued to get errors. This led me to further investigate the issue. I learned that imGUI requires an additional step that none of the other libraries I'd used so far required, and this step was to manually drag the files into my project. Once this was done, imgui finally initialized. Initially, I thought that implementing the menu system would be a breeze, but that was a very naive thought. After creating the test menu, it didn't take me long to realize that I could not interact with the menu at all. Turns out this was quite a complex issue, and I had to change the way I processed my inputs, more specifically, the camera controls. For a little more context, all my inputs are done through the glfw library, as that is a library responsible for creating the window object, and acts as a manager for OpenGL. This is a problem, because imgui also used glfw to handle inputs, and our input systems were conflicting with each other. After extensive research, I found the function responsible for this was the glfw set cursor callback function, but this function was also used in my project to track mouse movements. The correct way I learnt to handle tracking mouse movements was to use imgui's custom callback function, which would take my application custom inputs along with its own input handling system into account. Once the inputs were correctly processed, I could finally move on to creating the UI. In this code snippet, you can see the refined code that uses imgui's custom callback function. If right-click is held, the player will be able to look around the scene by moving and rotating the camera. However, soon as a user lets go of the right mouse button, the camera rotation will lock to the direction the user last faced. Once the user holds the right mouse button again, it will once again unlock the camera and pick up from the last direction it was facing. When planning out the overall design for my user interface, I knew that I wanted it to be easy to use and navigate. And as a result of this choice, I decided to organize all the settings for each particular object in its own drop-down menu. The image on the right shows the drop-down menu for the ELF model, and it has settings for positioning, rotating, and scaling the object. It also has an extra parameter called shininess. The greater this value is, the more shiny the model will appear. The image on the left shows the code that corresponds to the image on the right. Each parameter is manipulating one of the axes of the 3-fold vector for the desired output. To make the UI more easier to read, I chose to give each section its own subheading and made sure to add separators so the UI looks less cluttered and more readable. Throughout development, there were many features I had planned and hoped to have implemented within my project. One of these features are shadows. Shadows are quite an advanced technique, but I learnt the basic concept of how they would have been implemented. To implement shadows within this project, I would have had to use a buffer object, which is known as a frame buffer, also known as a FBO. Frame buffers are used often in games for not only shadows, but for creating post-processing effects, such as motion blur and depth of field effects. Just like any other buffer object, they are used as temporary storage locations, and in this case, they are used to store pixel information. This is important because to create shadows, you need to render the entire scene from the perspective of the light source, and create a depth map to calculate if an object is in a shadow or not. It does this by doing tests to see if another object is in front of the current object. If it is, the depth map fails and is marked as 1. This means it is within a shadow, and everything outside the shadow is marked as 0. Once this depth map is created, it is as simple as turning the depth map data into a texture, and applying it to the objects. And this would create a shadow that would dynamically move with the light. Within my project, I spent roughly 2 days learning this and attempting to implement it within my project. But after careful consideration, I chose to leave this out for several reasons. One of these reasons were time constraints. I wasn't sure if I was able to complete this feature in time to a satisfying degree without compromising the time I had to create this video. Another reason why I chose to leave out adding shadows in my projects was because, although I have a basic understanding of how they work, I still did not feel very comfortable enough using the frame buffers within my project when I do not fully understand how to correctly implement them, especially when they require a large chunk of my code to be restructured to accommodate for the second rendering pass to create the depth map. This image and GIF were taken from the earlier builds of my project. The GIF on the left was recorded on one of the very first prototypes of my project. Lighting was still not implemented yet, and I had just added camera functionality, which allowed me to navigate my 3D environment for the first time. The image on the right was taken on one of the very last prototypes I made. The scene was starting to be built, however, a lot of the models present in the final build are not yet implemented. A keen-eyed viewer may have also noticed there are two new categories within my UI, and these are Debug Cube and Debug Model. These settings help me to map out the coordinates I needed for positioning, rotating, and scaling my objects that were later present. Of course, these categories were temporary, and once my scene was built, they were removed. Overall, I am happy with how my project turned out, especially with the time I had to develop this. Although, I can't help but feel a little unsatisfied, as I really wanted to get shadows implemented and wanted to optimize my renderer before submission. One of the ways I would have optimized this is by reducing the amount of draw calls by instantiating my objects. This means that instead of individually drawing for each mesh, in particular my cube, it would be creating multiple copies in a single draw call. This saves on system resources and makes the application run better. After working on this project, I've learned a lot about graphics programming and about myself. I know that this is a subject area I am passionate about and want to continue to learn about and experiment in my own time, further developing this renderer I've created into a fully featured engine that I can use to build a game. But until then, I know I've only just scratched the surface of what this subject area has to offer, and I'm proud with what I've managed to accomplish. Thank you for watching.